In this homework problem, we're going to redo the same Brayton cycle gas engine, but we're going to use the air standard method rather than the cold air standard. In this case, we'll be looking at variable specific heats. So we'll be using the ideal gas tables. The numbers are exactly the same, so we can compare some of the differences in enthalpies and final result from last problem where I believe we got an efficiency of 48.2%. Right, so same problem, just a quick recap. If I draw a PV diagram, you have an isentropic compression process, state 1 to 2. That's for our compressor. Then we have constant pressure heating and heat exchanger, isentropic expansion in our turbine. And then finally, another heat exchanger, we have Q out and constant pressure isobaric. And again, this is a compressor, heat exchanger, turbine, and then another heat exchanger. And states 1, 2, 3, and 4. And our QN occurs here between 2 and 3. Okay, so very much the same as last one, so I won't go into as much detail, but in this case, the way we find enthalpy at state 1 is that the enthalpy is a function of temperature from the ideal gas table. So if we want H1, then we find enthalpy as a function of T1. So we go to table A22, which is the ideal gas tables for air. And I look up 300 K, which is my temperature. And so H1 at T equals 300 K. And I go over to the column that has enthalpy, which is the first column or column right after temperature. And I get a value of 300.19. I'm going to also find the relative pressure. So while I'm there in the table, the relative pressure, I go over 3 columns, it's called PR. And so PR1 is also a function of T1. And PR1 at T1 equals 300 K is 1.386. Kilojoule per kilogram. So 300.19 and 1.3860. Determine the relative pressure at state 2. So for an isentropic process, we have that PR2 over PR1 equals P2 over P1. And P2 over P1 is what we're calling our pressure ratio for this problem. So I can solve for PR2. So PR2 equals PR1 times RP. In this case, PR1 is 1.386 times RP, which is 10. So 13.86. And now, since this is still the isentropic process, I can find T2 as a function of PR2. So T2, where PR2 is now known as 13.86. If I look for that in the tables, 13.86. It is between 13.5 and 14.38. So I have PR2 values 13.50, 14.38. So my value is 13.86. And then there's 2 temperatures. corresponding to the two given values, which are 570 and 580. And so quick inspection, I'm going to be somewhere around 572, something like that. So this is my T2, and I interpolate to find that value. And interpolating, I get 570.08. And then the pressure at state 2 is simply given by the pressure ratio. So P2 over P1 equals RP. So P2 equals P1 times RP. And P1 was 100. RP is 10. So it's 1,000 kPa. Same as the previous problem. So really the only difference here is finding the enthalpy using the tables rather than an equation. Then again, now I have the temperature at state 2. So I can use that temperature to find the enthalpy. So now interpolating again, really I can use the same PR value. So I have an H, which is at 570, is 575.59. 580, 586.04. And so my H2 interpolate to find that value. And interpolating gives me 579.87. Right now to find T3, to do it the same way as in the last problem. So T3 over T2 is equal to V3 over V2, since the pressure is the same for both. So if I use the ideal gas law, cancel out pressures. And so this is what is RC. And so T3 is simply T2 times RC, which is the same as last problem. The pressure at state 3, P3 equals P2 because it's an isobaric process from 2 to 3. Then the enthalpy at state 3, now that we know T3 is the function of T3, where T3 equals, our given value from, I didn't calculate it, but let me just leave it as that. And then I use the ideal gas tables. And then finally, the relative pressure is also a function of temperature. Use the ideal gas tables again. And then at state 4, we have PR4 over PR3 equals P4 over P3, which is equal to 1 over RP. And therefore, PR4 equals PR3 divided by RP. And then to find the temperature, now I have PR4, so I can find T4 as a function of PR4 from the ideal gas tables. Just abbreviate that. And then H4 as a function of PR4 from the ideal gas tables. So once you know P4, you can find T4 and H4. And then the same way as we did before, mass flow rate equals AV1 over specific volume 1, where specific volume 1 equals RT1 over P1. And then just as before, I guess I skipped one thing, but P4 obviously is equal to P1. which is given 100 Q. And then the net work equals the work from 1 to 2 plus the work from 2 to 3. There's no work in the two heat exchangers, so didn't write those two terms. And then the only Q in is the heat exchanger between the coming out of the condensers, its inlet, and then going into the turbine, or out of the compressor into the turbine, that heat exchanger in between there, which is Q23. And then finally, the efficiency equals the network over Qn. And if you work out the numbers for this example problem, you'll find that the efficiency equals 45.67%. So this was for the air standard. And when we did the exact same problem as cold air standard, it was close, but it was 40, let's see. 48.2. So they're very close, a little bit lower for the air standard. So the more accurate one would be this one, but the cold air standard a little faster and also doesn't require tables.